Vlado Stilinovic. I see the co-chair Dominic is also here. And we have been given the pleasure and the honor of chairing this first session of the third installment of solid state science and research. And particularly because this gives me the opportunity to announce our first speaker for today, Professor Gautam Desiraju. Now, I don't think that anyone will say that I'm exaggerating if I say that there is absolutely no one on this planet who has anything to do with crystal engineering or solid-state supramolecular chemistry who would not know of Professor Desiraju and his work. Professor Desiraju quite literally defined crystal engineering as the field of study today. His 1989 book is well, something between textbook and Bible. I think that every group has at least one copy of it, and every young student is, I would say, not I would say forced to read it. They perhaps forced to start reading it, but they end up enjoying reading it. So it's not really that we have to force them a lot. Basically, this book has defined the field that, well, I mean, many of us here are in as a part of supramolecular chemistry, which has given it a very logical and very firm footing for further development, and it has really stamped the field since then on. Another thing which we also must mention is Professor Desiraju's work on weak hydrogen bonds. Also something which has ended in today. No one actually doubts in existence of CHO, CH-pi hydrogen bonds, that they do exist, that they are important contribution in structures of molecular crystals, and that they can be used in deliberate synthesis of given supramolecular architectures. Some 50 years ago, that really wasn't the case. Some of us probably have read the famous Donohue's "It Isn't" paper. So yeah, now we really do know that it really is. And one of the people who has contributed most to this is Professor Desiraju. We in Croatia have a very large halogen bond subculture. And from the point of view of halogen bond, again, we have much to be thankful to Professor Desiraju and his work on interhalogen contacts and halogen cyano group contacts in crystal structures, which was one of the bases of the renaissance of halogen bond, which we have had over the past 30 years. So without much further ado, I would now like to invite Professor Desiraju to give us his talk on crystal engineering, and I'm sure that we will all enjoy it very much. So, Professor.
So thank you very much, Dr. Stilinovic, for these kind words of introduction. I suppose everybody can hear me properly. Okay, now let's see. I have to go to the share screen, right? I'm going to try to bring up the presentation, if you just give me a moment. Do all of you see this? Okay.
Yes, thank you.
Okay, good. Let us start. Very pleased to be speaking with you, all of you. And it would have been nice, of course, to come to Croatia again. But COVID has seen to all that. And this afternoon, I would like to very briefly talk about the potential of crystal engineering. So this is not going to be a talk on some of the results and so on from the lab, although I will touch upon a few of them. So the general idea is in about 40 minutes or so. For 5 minutes, I will give you the background of the subject a little bit. And a recent example which illustrates some of the methodologies of crystal engineering. And then after that, we will go straight into the potential and possible future applications, because so many of you young people are in the audience. So you should really think much more than we did when we were your age, because the world has changed tremendously about science itself, where it is going, why one tries to do science, and for what purposes in general in a large sense. The so-called ivory towers of yesteryear, not strictly valid anymore. So while we must maintain our quality and scientific rigor, one must keep a lookout for how things are likely to pan out. And I will also say about this COVID thing, nothing in this world is going to be the same after this COVID. It is not like that Spanish thing of 100 years ago. So we all have to be prepared to change our ways of thinking, and that is true for scientists also. So this crystal engineering, so crystal means the solid. Engineering means design. And then we have interactions. Then we have this understanding again. Then we come back to design. And then properties, desired properties. So it's a way of making things. Chemistry is all about making things. Making crystals so that they do some things. And Dr. Silinovich mentioned my 1989 book. And the definition I gave there is very broad. And it is because, well, not because, the definition was broad and still it was accepted by the community. But because it is so broad, the subject has become diverse. And so the thing about crystal engineering today is that it is very diverse and it brings in many people from many different areas of science. So it is also keeping with the general mood of SCIRES, because Professor Zagreb mentioned that there were people in different areas. Now, this doesn't matter so much for crystal engineering. The more the number of areas, the better. And it has become of very great relevance today. Now, purpose of this lecture is to see how and why some of these things happen. Now, the core problem with the subject, it has always been the core problem, is that the crystal structures cannot be predicted easily from molecular structures, at least not with modular approaches. Like imagine if there are 10 people sitting in a room and each of the people are looking at all the other 9. And so when a person starts a discussion, he tries to look at what the other 9 people are thinking maybe before he or she starts speaking. So, and if everybody is looking at everybody, then it becomes a problem. So that is why crystal structures are difficult to predict. You can't get it just from taking the functional group separately. So crystal structures are not related to molecular structures easily. Now we've seen so many examples in our research, but I just pulled this out. Professor Zagreb said fun, and this project was actually done for fun. is certainly the strangest example that I have come across in our own work. We all know that carboxylic acids, at least many of them, tend to have this syn conformation between the OH group and the carbonyl group. This is very common. We also know that the syn conformation tends to form these dimers. Sometimes, not so often, there is an anti-conformation too for acids. Not so common. But here we have this unusual group of structures where we have both syn and anti in the same structure. This is very, very, very uncommon, weird almost. And in a whole family of cubanes, we saw this again and again and again. Mention was also made of some of our work on weak hydrogen bonds. Now look, this cubane thing is very activated. And therefore, this CHO bond is unusually strong. It is so strong that it can make all these things look weird. So one guy in the room is influencing the discussion among the other people. So clearly in this kind of situation, a simplification is needed. You can't do it like this. You cannot take each crystal structure and try to analyze it in terms of the molecule. It will take too long. So that's why we need the synthon. The synthon is some kind of a summary or opinion of 2 or 3 of the influence makers in that room. So if we get an idea of how those discussion leaders are behaving, then we get an idea generally of how the rest of the crowd will behave. And that is the whole principle behind synthon theory. And it works so well because these crystal structures are emergent properties. So I'll not say anymore because these are all very well-known things. Now, a mention was made of interactions also, these hydrogen bonds and so on. Recently, halogen bond, more exotic, and it is now being used in crystal design. So many things. So these are all different languages which these 10 people are speaking to each other in. Some language will become stronger after some time. So that's the way it goes. So when usually we try to bring in a combination of interactions, the more complex the structure you want to make, the more difficult the synthetic target, the more variety of interactions you need. Now, we showed this, of course, recently in some of these multi-component molecular solids. Here are 2 more different molecules in the same solid. And then here you can make it 3. You can even make it 4. All different. Stoichiometric. No ions, no metal ions, no nothing. Just neutral organic compounds. 4 different things you want to get them together. So at each stage, this becomes much, much more difficult. And without synthon theory, of course, you can't do this. And this was this known example which I was going to give from what could be called a fundamental kind of crystal engineering work. So stuff which has no application immediately. You need this kind of work also, by the way. You can't just have only application-based work. You need to do work, you need to publish papers where there's no application. You take a synthetic target that's extremely difficult and you try to make it. Now, why do you try to make it? So that in the process of trying to make it, you get some new methodology. Now look at these. These are some molecules. But this TMP exists in 2 different environments in the crystal. When it is like this, then you can replace one of them with something else. You see? And then these 2 are the same molecules, but again in 2 different environments. So this can be replaced by this. So as you can see, with this PAH being a polynuclear aromatic hydrocarbon, something that forms some CH pi interactions with TMP. So very quickly you can go from 2 to 3 to 4 components in a crystal. And here they are actually. This is tetramethylpyrazine. This is 2,2-bipyridine. This is resorcinol. And then this is dipyridylethane. So you see, you can get these four things stoichiometrically. This is the general idea. So I'm going to stop this pure crystal engineering, publication-oriented work with this example. It's enough. We can do the same thing. Recently, last month, I think we published something in Angevante on these halogen bonds. So you can make ternary co-crystals using only halogen bonds. And one of the referees said they've made their job more difficult and tried to tie their hands behind their backs if you don't want to use hydrogen bonds at all. Yes, why do you make it more difficult? For the same reason, to develop some more synthetic methodology. Can you make higher co-crystals without hydrogen bonds? That's the kind of challenge you have to pose to yourself. The questions you pose to yourself are much more important and interesting than the questions you pose to other people. So now we come to the future. Now, we have some very big problems in the world today: health, energy, environment, water. These are the huge pressing issues of the day. And we need to do our science so that directly or indirectly it is geared towards solving some of these big problems. So I have chosen 5 where crystal engineering is particularly important. The question of solid forms of pharmaceuticals, solid state reactions, which also includes mechanochemistry. Then little crystals with big properties. And what are these kinds of properties? Then, of course, the framework solids, WAFs and COFs. And finally, the energy question, property engineering, solar energy, etc. So the idea is in a couple of minutes to say a little bit about each of these things. And I noticed also from the book of abstracts that many papers and abstracts on all these topics. Let us go to these pharmaceutical co-crystals. It's been a nice journey. So from supramolecular synthon, you can go to co-crystal, and then you can go to pharmaceutical co-crystal, and then you can go to formulations, and then you can go to a product. So it's been pretty quick actually if you think about it. About 20 plus years to go from synthon to Entresto. So yes, you mean these co-crystals are very important, trying to put different shaped objects in the same place in a close packed fashion. It's quite an intellectual challenge also. And so here we have the good and the bad. The bad are the 2011 FDA guidelines, which in the face of mounting scientific opposition was replaced by the 2018 guidelines. And this has really opened up the way for pharmaceutical co-crystals because they say that it provides opportunities for engineering solid state forms. This engineering word has come beyond conventional solid state forms such as salts, polymorphs. So it's really opened up the way for co-crystals. Now, why are these co-crystals important? See, it's because many of these modern techniques of drug design produce lots of drugs which are in this so-called BCS class 2 category. They are very lipophilic. So while they are permeable, they are not very soluble. So one of the big questions is to increase solubility of the solid drug forms. 80% of the drugs we take are anyway in solid forms, solid tablets, powders, suspensions, ointments, and so on. So solubility and permeability are big questions. And this is where co-crystals come into their own because many of these pharmaceutical co-crystals, the solubility goes up relative to the pure APIs. Very briefly, one of our papers a few years ago, you have this antibacterial and this antimicrobial. This is very insoluble. It's BCS class 4. And you see, it's very insoluble, except in highly acidic media, it is norfloxacin is insoluble. Sulfadiazole is not so bad. But you see, in the co-crystal, the solubility of norfloxacin increases always. Yeah. And look at the permeability also. This is norfloxacin by itself. This is sulfathiazole by itself. And now you see the co-crystal. So something is happening here. This co-crystal does not behave like a physical mixture of norfloxacin and sulfathiazole. And the first proper evidence we got for the viability of this inthon in solution, because if everything dissolves instantaneously, when you take the co-crystal, then the norfloxacin and the sulfathiazole will be well separated from each other. And through the membrane, sulfathiazole, which is permeable, will go through and norfloxacin will get stuck. In fact, we can see this. When you take a physical mixture, dissolve it up nicely, and then put it across a membrane, you see the norfloxacin literally crystallizing on the surface of the membrane. Now, when you do it with the co-crystal, both these things go through. So, which means we must invoke the viability of something like this, which is an extended hydrated supramolecular synthon. So, there is some synthon memory in solution in the early stages. It's very important. And it forms the basis of much of what is going on in co-crystal work today. And this is why it's going to be very, very important. And it's, if you look at it, as far as marketed drugs are concerned, polymorphs, solvates, hydrates, salts, even eutectics have been there for some time. But suddenly in a hurry, you are getting lots of co-crystals in the market. And I foresee a time before long where a co-crystal becomes the default option to market a drug. It won't be an option that is used as a last resort option. So there are many, many advantages in having co-crystals. So this is one of the 5 corners of my pentagon, which I put up, these pharmaceutical co-crystals. Now we come to solid state reactions, mechanochemistry. Of course, I must invoke the name of Gerhard Schmidt, who actually gave us the name crystal engineering. I might have defined it in a certain way in '89 and broadened the scope, but the name itself, well, strictly speaking, he didn't give the name. A man called Lipinski gave the name in '55, but it was the work of Schmidt in the '50s and '60s that put it on a scientific basis. And I feel nostalgic when I look at this physical meeting which was held in the Weizmann Institute to celebrate his centenary of his birth, just a few months before COVID. And it's one of the last international meetings I attended, or the last meeting, I should say. I have not been outside my home for 14 months now. So, and here it was. I mean, if you can see the thing, it says 23rd to 24th October 2019. So there were already COVID cases floating around in China and God knows where else. And so we didn't even know what was happening and feeling quite nice in the meeting. And a tribute to a great man. And so it goes. Now, mechanochemistry has become very big now. There's so many big names here. Maybe 1 or 2 of them are even in the audience, I do not know. So the whole idea about solid state reactions mechanochemistry is that it's a study, systematic study of diffusion in molecular solids. So this is not the chemical symmetry of Ruzicka, but molecules do move. They move quite nicely also sometimes. And so how can we exploit this whole business of liquid assisted grinding? It is used in the co-crystal technology, of course, but how does it work? Why does it work? We still don't know. And then this polymer assisted liquid assisted grinding, POLAG. I was looking up this POLAG and suddenly I found that it was actually a word in Serbo-Croatian or something. Is it? Does it mean next to or something like that? It says there was a meaning in Serbo-Croat, but since I don't know your language, I just let it go. So this mechanochemistry thing it's very important because many of the industrial reactions are still actually run in a solid state way. And many of them proceed like this. The stuff is all shrouded in the patent literature. These new reactions have a future because they're cheaper to run. They don't involve solvent and they are less exposed. The operators are less exposed to the solvents in the reaction medium. So I think we're going to see lots and lots of solid state reactions using the principles of mechanochemistry that have been laid down so far. I mean, I've spoken about one pioneer. I would be remiss if I did not speak about three more giants in the field of solid state chemistry. And I've had the pleasure to know all of them and interact with all of them over many years. Much of Fumio Toda's work was not understood properly in his lifetime. And a great many of these organic transformations can be run using the methods he described. And I think some of these things have to be looked into now using the present day methodologies. And then again, I would be remiss if I did not mention the name of Professor Raghunath Prasad Rastogi of the University of Gorakhpur in India, who in the 1960s, in a famous paper in the Journal of Physical Chemistry, gave us the essence of solid state grinding. And Professor Rastogi, of course, he passed away 3 years ago at the ripe old age of 92. He was quite active till the end. Great man, another giant in the field. And then here is my third giant, Professor Vyacheslav Vladimir Goldirev, who at the age of 94 is still very much with us. And he has written this beautiful paper, co-authored with his daughter Elena and so many other people, about mechanical alloying, mechanochemistry, what's in a name. Yes, indeed, what's in a name. So it's been my great privilege to know all these three people. And they are the people who actually set many of these things. I think we should look back at some of these things, what these pioneers have done. And I'm sure this is going to move forward in a very nice way. Now we come to the related thing. Now here in solid state reactions, we spoke about huge reactions done on a kilogram or ton scale. Now we are worrying about big properties in very small crystals. So this business about mechanical properties of crystals. We wrote a review a few years ago. We tried to define some of these things. Brittle means something that is not tough. Plastic means something that is not strong. And elastic means something that is not stiff. So in the English language, tough, strong, and stiff could all mean the same thing, but in the subject, they mean something quite different. And I'm disturbed to see people misusing these words, saying whatever they like. Please don't just go to some Google and download something and put it in your paper. It's not nice. And so we wrote this review, and there's a flurry of, not papers, reviews by so many people. Professor Naumov, who's going to speak immediately after me, I suppose. And then Professor Sun in Minnesota, Professor Chandrasekhar in Hyderabad, Tomislav in McGill, and Sushoban Das and others, Kitagawa and Bardeen in USA. And most of all, I'm pleased to see a review, beautiful one, on elastic crystals written by two of my former associates, Saumyajit Ghosh and Manish Mishra, both of whom are in independent faculty positions in India today. So, I mean, these are not papers, as I said, they're reviews, so many reviews in just 3 years. And this means that these are all reviews that largely cover their own work. All right. So it means these are all highly personalized reviews, very, very important. This is exploding field. And sharing, of course, we saw long, long ago. And Professor Mallaredi was a graduate student in my group. So you can see the shearing of a crystal. So this is what happens. It's an example of a plastic deformation. And this is elastic. So plastic means, okay, let's go back here. Plastic means that one set of interactions is a bit weak compared to the others. And so that is the fault in the crystal, and that's where the crystal yields irreversibly. For elastic deformation, we take these red lines here, which I've put, red things. Let's say they're aromatic rings. Now, can you separate the distance between these rings, and therefore it means can you bring others close to each other? And similarly, can you do this where you change the angular deformation? If you can do all these things easily, the crystal is elastic. Very recently, we had a nice example where you can actually go from 1D plastic to 1D elastic to 2D elastic to 2D plastic. And this last illustrates the fact that you can have the same structure and different properties. Usually we are used to thinking of structure and property as, coexisting always. Structure equals property, property equals structure. No. You can have the same structure and different properties simply by modulating the interactions. I told you, in that room with all the people sitting there, people talking in different languages. So if you modulate those two languages somewhere, then you can do all these tricks. So as I see this crystal engineering business, we went from molecular structure to interactions, try to understand what structure gave what interactions. This was in the 80s and I think early 90s, just analysis of the structures. Then the second stage started with this synthon business. So working backwards from a crystal structure, retrosynthesis, you define the structure you want and you then figure out what interactions you need to get the structure. That's the point. So that is the second generation in my view. Now we are very much here. You want a property. And instead of saying crystal structure, here I've got a crystal structure, let me see what property it has. No. You define an important property and then say work backwards again. If I want this property, therefore what structure do I have to make? So you see the thinking and the order of the logic has changed over these three generations. And this brings me directly to the question of morph, which is the fourth point on my pentagon. So this blue thing here, here and here, this is Prussian blue, which is one of the first examples of a coordination polymer, 200 years plus. And so framework, 3D porous solids. The important names are Richard Robson, who gave us the retrosynthetic approach to a morph. Largely like what I did for organic crystals with the synthon. So he still used the word coordination polymer. Omar Yagi gave the name metal organic framework a little later. So many compounds, 20 years. They're very easy to crystallize. I suspect because they're so easy to crystallize, it's very easy to do a crystal structure, and that's why you had so many papers. And so many papers, so many citations, everything. So it sort of explodes. They are characterized by very large internal surface areas compared to zeolites. They're capable of acting as acidic catalysts. And they can be used for separation and catalysis, basically. So you can remove CO2. You can, for example, remove acetylene from ethylene. Kitagawa has shown how it can be used in biomass conversion. So much of work. I think Professor Farha is going to tell us much more about this category of compound tomorrow. And but of course, there's a big problem. And this was brought home very nicely in this article in Chemistry World. For the last 15 years, the elephant in the room has been, where are the applications? So by applications, I don't mean small things, I mean huge things. Like Haber's process, Ziegler-Natta catalyst, non-steroidal anti-inflammatory drugs, Heck reaction, things like that, that change really the way in which industry itself starts working. Now here there are some problems, lack of thermal stability, limited chemical stability, water sensitive. Some of them are made which are not water sensitive. Multi-use industrial environments, zeolites rule the roost. You have to read zeolites. You want to use these things for catalysis and separation. So they say the big ticket applications are missing. So we'll hear what Professor Farah has to say tomorrow. But there are problems. Definitely, you have problems in this, and I illustrate with respect to CO2 and CH4. No doubt that CO2 emissions are a huge problem, and MOFs will capture CO2 nicely. But stoichiometrically, the molecular weight of the MOF is 10 times that of CO2. So you need lots of MOF to take up not so much of CO2. And the CO2 is not just CO2 as is, it is mixed with all these dirty things. PM, soot and stuff, high temperatures. We know they are not temperature or water stable. They are not recyclable. The present classical way of removing CO2 is this alkaline scrubbing, which is still cheaper than this. So you see, these are all problems. Now with this methane as a fuel and MOFs as a transporting agent for methane. Now here there is another problem. So you have to look at the finances and the economy of the thing. Now today crude oil is 50 to 70 US dollars per barrel. Even at this price, methane is still fairly cheap. And so why do you need all these fancy things? And a few years ago, of course, we all know crude was much, much cheaper. In that case, there's no question even of thinking about it. And even the question of crude oil, it may be that before long, crude oil is not so important. I mean, the amount of natural gas that Qatar and Turkmenistan are sitting on today, before long they'll be laughing all the way. And the Saudi politics and actions themselves are reflective of the fact today that crude oil is not going to be the number one fuel for the whole world. So all this needs to be factored into when you start thinking about applications. And as I said, it is very, very important. I emphasize again, whether you are into crystal engineering or any other technique, there's no point saying, I have a structure. Here, look at my structure. So now let me find the property. No. You first go to the property. What do you need to solve? What is the problem you need to solve? And from that, you work your way back to the structure. The third generation, if you remember the retrosynthetic arrow, property comes before structure. I think that is the lesson here that all of us need to know. So yes, real big time applications. I've seen some very nice papers on the extraction of water in the desert regions using MOFs. So you be in this desert and it will absorb, the MOF will absorb the water, and then there's a nice tap and all that, you open it and then the water will come out. This is very nice. because in a desert, water is a valuable commodity. But this may not be the problem. See, I live in a country where we have a big water problem. 1.3 billion people, so we are always going to be short of water. But our problem is not enough water, but is water at the wrong time. The monsoon has just started in Bangalore. By the way, the monsoon starts about here and then works its way up over 2 months all over the place. So Bangalore is about right here. So the monsoon has started on time and it dumps water on us for 3 months. Dumps. After that, no rain. So the problem is not no water, but no water at the time when you need it. And so we have had very, very ancient systems of water storage and water preservation. Many of these things were destroyed purposely by the British during the colonial era. But now they are starting up again now. Now here I am actually, I'm not bluffing, I'm near one of these places. And this is roughly about here, which is about 700 kilometers from Bangalore. So you can see what a big country we live in. This little thing is 700 kilometers. So this is water storage. We also have desert regions. This is all desert. Okay. This is a cold desert. I know people who are trying to grow plants in this cold desert area. And how did we handle this desert water problem? Look at our 100 rupee note. This is an underground well actually. This is a well in this desert region. It's right about somewhere here. It's called Vav. And it's not that there is no water in the desert. It's just that it is inaccessible. And these are not uninhabited places. There are people living there. When you look at a market, India is a very big market. But we are not likely to buy a MOF-based thing which can get water out of a desert region. So one must look also at the market before you start thinking about products. So I would say that even look at the market before you even think about the product. I think all these things have to be factored in simultaneously. By the way, it's a big map. This is a geography map. This is where Professor Rastogi used to work, by the way, very far away from here. Anyway, so coughs. Rahul Banerjee wrote a very nice but realistic perspective in JAX 2 years ago. These are very big problems: scalability, stability, processability, and he talked about it in an utterly realistic fashion. We still have a ways to go with these coughs. There's no point jumping the gun and say, I've got this, I've got that, I can solve the world's problem with coughs. Please work out the science, work out the market, work out the demand, and see if you can do much better than anything else which is there. Then start talking. Otherwise, I'm afraid if we do some of the things we are doing now, the general public will stop taking us seriously. And industry will stop taking us seriously. That is of immediate concern to us, because so many of us are funded in a smaller or larger part by industry. So yes, we can go on and on. They say they can do lots of things, but even of those three things, that processability is a difficult problem, because many of these coughs are all highly fluffy things. At least that's what Dr. Banerjee says. Finally, we come to the last of these 5 things: solar energy, functional materials. This is huge, because this is something, it's an area where we have made much progress. And just like zeolites are the things to beat for catalysis and separation, the perovskite-based solar cells are the things to beat if you are going to think of having an organic photovoltaic. Mind you, organics have their advantages because of the variety that is implied in organic structures. You can really modulate these things nicely. So it might be useful for niche applications, wearable electronics, sensor devices, medical diagnostics, things that you actually wear and go about. Solar harvesting of lower energy output. But once again, this is an area which I think we need, scientists have to put in a lot of pure research first. Because there's no doubt that by 2030, electricity is going to be so cheap that it's going to be practically free everywhere in the world. I think already I'm told there are countries like Germany and the Netherlands where it is actually quite cheap now. Now I see when I travel in India all over the place, I see both this and this. And some parts of India are doing, we're doing both solar and wind really well now. So this is some place where people who are working with molecular solids must try to get into, because these are things where we can actually maybe teach them things. It brings me back again to, I saw some of these papers on polythiophene. Interesting molecule. It can assemble plane to plane, like so, or plane to edge, like so. And the films themselves can be laid on the substrate plane to plane or edge to plane. And so all these things give varying, charge carrier mobility. So the behavior as photovoltaics is different based on how you can control, how you can design. And so crystallization under various conditions, something we need to be able to control very well before we can anywhere into trying to take on the perovskites. These are very old pictures. I remember the old work on herringbone and sandwich herringbone and so on, where we took up from Robertson's old classifications of the 30s and 40s. See, in science, the same thing comes again and again. It comes in different forms and shapes. But essentially, at the end, it's the same thing. So if we learn to control herringbone, sandwich herringbone, gamma and beta, if we learn to control these really well, you could solve many of the problems here, which have to do with photovoltaics. And so this is another thing which people should start looking at. And, that's about really what I wanted to tell you today. And as you can see, I don't know what you'll expected, whether some latest result, this is the latest thing from my lab and the postdoc has just brought this to me, so it's hot off the press. No, nothing here is hot off the press. So, but I think these are things that can be hot off the press day after tomorrow. But I think the main idea is that the basic ideas that many people in this crystal engineering subject have put forward over the last 20, 25, 30 years, they now need to see a new kind of shaping up so that we more aggressively address industry, address the market, and address society in general to tell them that in the end, after this whole COVID mess, have told us that, I tweeted this morning, scientists, we really need to introspect seriously. I will say it loud in a public meeting like this. Lancet and Nature, their behavior has been disgraceful in this whole episode. And so there is no point in saying that, oh, all this is nice, that is nice. When some of the big things are not nice, you should say it. And scientists, people look upon us as role models in society. When I go around in India and, and tell a lay person that I'm a scientist, I can see the way he or she looks at me. There's a certain amount of respect. We scientists should not lose that respect in doing all sorts of crazy things and trying to become popular in a hurry. And I feel that this is really what I wanted to tell. I've been in this field for a long time, and I have seen great many people, great many situations. Of course, many of the things I saw were in much more innocent times. But I would think that youngsters should have a keen look Many of you people are much more intelligent than what we were when we were your age. I have no doubt about that also. But then you need that intelligence to cope with the world such as it has become today. And I hope, therefore, that you take my remarks in the right spirit. I don't think we have time for any questions, Vladimir. So we will skip the questions. Anybody who has any questions, please address the questions to me by email or by Twitter. And you will get usually a fairly rapid response. So having said this and not wishing to impinge upon the time of Dr. Naumov, I would like to thank you all very much for your kind attention.
Thank you, Professor Desiraju. We might have time for one or two quick questions if someone is interested.
Okay.
I don't see any hands up. Okay. Okay. So thank you, Professor Desiraju, once again.
I may have a question.
Sure.
Yeah.
Who is speaking, please?
Kruno Ujarovic.
Oh yeah, sure.
The thing is that I don't know how to raise the hand. That's the vidim. So the question is, what do you think about the let's say the future of crystallography and crystal engineering with these advances in instrumentation and in computational methods? Where do you think that can lead us? And
you see, with the importance of lower dimensional structures, films, and so on, other diffraction-based methods will come in and they will become more important. Small angle diffraction, electron diffraction for sure. I mean, electron diffraction is going to become so important. And this small company in Switzerland, I think, Dr. Hovestrait is running it, or I've forgotten, LD Co or something. They have actually got a diffractometer, electron diffractometer. So this is going to be hugely important. So any ways of looking at less ordered media. See, we are used to thinking of some big single crystals and then some amorphous and then nothing in the middle. But much of the interesting chemistry comes in the middle. Maybe Rusitska is correct that the crystal is dead. So we have to learn how to look at this intermediate region between fully amorphous and fully crystalline. Yes, we should worry about crystals diffraction. But you know, just like how we have a branch of the subject called cryo-EM. Cryo-EM involves no diffraction. And yet it is considered a part of crystallography today. In the same way, I see a stage when crystal engineering will not need diffraction, but it will still be very much considered a part of crystallography. So I hope that answers your question, at least in a philosophical way.
Yes, for sure. I wanted to hear your opinion. I think we are sharing it mostly, yeah. So thank you very much. Thank you, Professor. Thank you for the lecture.
Okay, you're welcome.
Okay. You have any other questions? Okay, apparently not. So, thank you, Professor Desiraju, once again. And Dominic, will you be?
Yeah, it's my turn. I see Panche is already ready. Well, I will introduce very briefly.